The heart of our solar system, the sun. This blazing ball of plasma dominates our sky. It is the anchor of our solar system. All planets, including Earth, orbit the sun. Its gravity holds everything together. The sun provides us with light and warmth. It is the ultimate source of energy for almost all life on Earth. Without the sun, our planet would be a lifeless, frozen wasteland. Its influence extends far beyond just providing light. It shapes the orbits and destinies of every object in the solar system. Understanding the sun is key to understanding our place in the cosmos. The sun is not just a static object in the sky. It is a dynamic and active star. It goes through cycles of activity with periods of relative calm and intense outbursts of energy. These cycles and outbursts can have a profound impact on Earth. This is why you need to understand the sun's composition. The sun is mostly made up of hydrogen and helium. These are the two lightest and most abundant elements in the universe. About 70.6% of the sun's mass is hydrogen. Helium makes up about 27.4%. This leaves just a small fraction, about 2%, for heavier elements. These heavier elements include oxygen, carbon, neon, and iron. Even though they are present in small amounts, they play a crucial role. These trace elements are remnants from previous generations of stars. They are the building blocks for planets and even life itself. The sun is not a solid ball of fire. It is more accurate to think of it as a giant ball of plasma. Plasma is a state of matter where atoms are stripped of their electrons. This creates a sea of charged particles that are constantly moving and interacting. Deep within the sun's core, a process called nuclear fusion takes place. This core is an incredibly dense and hot region, reaching temperatures of around 15 million degrees Celsius. It's here that the magic happens, where the sun's energy is born. This is the engine that powers the sun, driving its immense energy output and fueling the light and heat that reach us on Earth. In nuclear fusion, hydrogen atoms are fused together under immense pressure and temperature to form helium. This process is not easily replicated on Earth, but scientists are working tirelessly to harness this power for sustainable energy. This process releases an incredible amount of energy, far more than any chemical reaction could produce. It's the reason why the sun has been shining for billions of years. Imagine squeezing two hydrogen atoms together with unimaginable force. The conditions in the sun's core are so extreme that these atoms overcome their natural repulsion and merge. The result is the creation of a helium atom. This fusion process is the source of the sun's energy, and it's a cycle that continues relentlessly. But here's the catch. The helium atom has slightly less mass than the two hydrogen atoms combined. This difference in mass is crucial to the energy production. This tiny difference in mass is converted into a huge amount of energy following Einstein's famous equation E = mc squared. This equation shows that even a small amount of mass can be converted into a large amount of energy. This energy is released in the form of light and heat, which are essential for life on Earth. Without this energy, our planet would be a cold, lifeless rock. It radiates outward from the sun's core, traveling through the various layers of the sun before reaching the surface. The energy then travels through the different layers of the sun, including the radiative and convective zones, before it finally escapes into space. Eventually, it reaches us on Earth as sunlight. This sunlight is crucial for photosynthesis in plants, which forms the base of our food chain and provides oxygen for us to breathe. This process has been going on for billions of years and will continue for billions more. The sun is currently in a stable phase of its life cycle, but it will eventually evolve and change, affecting our solar system in profound ways. Exposing the secrets in the sun's layers. The Sun, our closest star, is a fascinating celestial body that has intrigued scientists and astronomers for centuries. Understanding its structure is key to comprehending many of the processes that govern our solar system. The Sun is not a uniform ball of plasma. Instead, it is a complex, dynamic entity with multiple layers, each contributing to its overall function and behavior. It is structured into distinct layers, each with its own unique characteristics. These layers work together to produce the energy and light that make life on Earth possible. Think of it like an onion, with each layer playing a specific role in the Sun's overall behavior. Just as peeling an onion reveals its many layers, studying the Sun's layers helps us understand its inner workings. At the heart of the Sun lies the core. This is the powerhouse of the Sun, where the most critical processes occur. This is where nuclear fusion takes place. In the core, hydrogen atoms are fused together to form helium, releasing an immense amount of energy in the process. Temperatures here reach a staggering 15 million degrees Celsius. This extreme heat is necessary for the fusion reactions to occur. The core is about 20 to 25% of the Sun's radius. Despite its relatively small size, it is the source of all the Sun's energy. Surrounding the core is the radiative zone. This layer plays a crucial role in transferring energy from the core outward. In this zone, energy travels outward in the form of photons. These particles of light carry the energy produced in the core to the outer layers of the Sun. These photons can take hundreds of thousands of years to make their way through this dense region. The journey is slow because the photons are constantly absorbed and re-emitted by the surrounding plasma. Moving outward, we encounter the convective zone. This layer is characterized by turbulent movements and plays a different role in energy transport. Here, energy is transported through convection. Hot plasma rises towards the surface, cools down, and then sinks back towards the interior, creating a continuous cycle. Hot plasma rises, cools, and then sinks back down. This process is similar to boiling water in a pot, where the hot water rises to the top, cools, and then sinks back down. The convective movements are responsible for the Sun's dynamic surface and the formation of sunspots and solar flares. Finally, we reach the Sun's visible surface, the photosphere. This is the layer from which the sunlight we see is emitted. This is the layer we see from Earth. The photosphere is about 500 kilometers thick and has a temperature of around 5,500 degrees Celsius. Above the photosphere lies the chromosphere. This layer is less dense and hotter than the photosphere. The chromosphere is a thin layer of the Sun's atmosphere. It is only a few thousand kilometers thick, but plays a crucial role in solar phenomena. It is visible during a total solar eclipse and appears as a reddish glow. This glow is due to the presence of hydrogen gas, which emits light in the red part of the spectrum. The outermost layer is the corona. This layer extends far beyond the Sun's surface and is much hotter than the underlying layers. This is a vast, extremely hot region of plasma that extends millions of kilometers into space. The corona's temperature can reach up to several million degrees Celsius. It is usually only visible during a solar eclipse. The corona's high temperature and low density make it a unique and intriguing part of the Sun's structure, influencing solar wind and space weather. The Sun is not a constant star. It is a dynamic and ever-changing celestial body that undergoes various phases of activity. It goes through a regular cycle of activity known as the solar cycle. This cycle is a fascinating and complex process that influences not only the Sun itself, but also the entire solar system. This cycle lasts approximately 11 years and is characterized by the waxing and waning of sunspots, solar flares, and coronal mass ejections. These phenomena are driven by the sun's magnetic field, which undergoes significant changes throughout the cycle. At the beginning of the cycle, solar activity is minimal. The sun's surface appears relatively calm with few disturbances. There are few sunspots visible on the sun's surface. These dark spots are regions of intense magnetic activity and are cooler than the surrounding areas. As the cycle progresses, the number of sunspots increases. This marks the rise in solar activity with more frequent and intense magnetic disturbances. The sun's magnetic field becomes more complex and tangled. This increased complexity leads to more dramatic solar events. This leads to an increase in solar activity. Solar flares, which are sudden bursts of energy, and coronal mass ejections, which are massive bursts of solar wind and magnetic fields, become more common. At the peak of the solar cycle, known as solar maximum, sunspots are abundant. The sun's surface is dotted with numerous dark spots, indicating high levels of magnetic activity. Solar flares and coronal mass ejections occur more frequently. These powerful events can release vast amounts of energy and charged particles into space. These events can have a significant impact on Earth, disrupting communications, damaging satellites, and even causing power outages. The charged particles can interact with Earth's magnetic field, leading to geomagnetic storms. As the cycle progresses towards solar minimum, sunspot numbers decrease. Solar activity gradually subsides. The sun's surface becomes calmer, with fewer disturbances. The sun then enters a period of relative quiet before the cycle begins anew. This period of low activity is known as solar minimum, and it is a time when the sun's magnetic field is less complex and more stable. Scientists have been studying the solar cycle for centuries, using various tools and techniques to understand its patterns and effects. Observatories around the world monitor the sun's activity, providing valuable data that helps us predict and prepare for solar events. With advancements in technology, we are now better equipped to forecast future solar cycles and their potential impacts on our planet. Understanding the sun's rhythmic heartbeat is crucial for protecting our technological infrastructure and maintaining our way of life. Observing the sun in different wavelengths of light reveals the intricate details of its activity. Instruments like the Solar Dynamics Observatory provide stunning images that help us visualize and comprehend the dynamic processes at play. The sun's influence extends far beyond its surface. Its activity affects the entire solar system, from the solar wind that shapes planetary atmospheres to the beautiful auroras that dance in our skies. The solar cycle is a testament to the sun's powerful and ever-changing nature. As we continue to study and learn from the sun, we gain a deeper appreciation for its role in our universe.